Okay, this is now day 17 for segments in a circle. And now I want you to notice the difference here. We still have they're intersecting outside. We have one of our segments is a tangent line. Remember, a tangent line is one that just hits the circle at one spot. These segments before were intersecting the circle at two spots. Okay? So again, we want to come up with some formula for PA, PC, and PD. And similar to what we've done before, what I'd like to do in some different colors is draw a triangle. And here I'm just going to draw one dotted line. Actually, that's not true. One dotted line here. And a dotted line here. And importantly, what I'd like you to see or focus on is this arc right here. We know that angle D over here, this inscribed angle, creates that arc, this arc AC. Okay. But also, look at point A and specifically this angle PAC. That is also an inscribed angle. We learned a couple of weeks ago with this inscribed angle and this arc, those are both the same. So we can actually say that this angle right here, PAC, is congruent to this angle right here because they both create this arc AC. Okay, so again, angle PAC is congruent to angle D, right? Because they both create this, they're both inscribed angles that create arc AC. And if we think about the two triangles, this shows up in both. So I can then say that triangle PAC is similar to triangle PDA. P shows up in the same spot. D and A we just talked about above. And then C and for the bigger triangle. So notice that there's kind of two triangles going on. We've got PAC. I'll do it in red. It always is a little bit dangerous. So starting at point going to A and C, this triangle. Okay. And then is congruent to, do I even have any other colors? Not really. Let's try purple. Thanks. We've got P going to D, so P to D to A. So they're clearly not the same size, but they are similar. Okay, so I'm going to go back to blue. Now, because I can make this statement, I once again have proportionality. So P over A, first over PD equals second AC over my second one here, DA, equals first and last PC over PA. This time I did write them kind of in the order, but notice where my dotted lines were. My original dotted lines were AC and AD. I don't really care about those. Remember, those weren't my original segments. If I were to reverse and erase all of this stuff, these ones I don't really care about. What I do care about is this ratio and this ratio. So if I cross multiply, I have PA times PA equals PD times PC. So it's really this tangent line times itself equals PC times PD. And there's a lot of colors going on, so let's draw it again using our favorite PQRS. And let's go here and here. And so if we have, this is P, and this is let's say R and S, I guess. Well, we have P times itself, P times R. That's the PC part outside, but PD is the whole thing. So it's R plus S, the critical thing. It's not R times S, it's R squared equals r times r plus s. And that is our formula for when we have an intersection outside when one of them is a tangent line. Okay? So let's just kind of, this is the one you want in your notes right here, and let's try a couple of examples. So again, our formula says outside part times the whole, what I like to think about it is for the tangent part, it's the outside part times the whole part. So it's again 100 x squared equals outside part 32 times the whole part 32 plus the 18. So we got 32 times 50. So we got 100 x squared equals 1600. X squared equals 16. X would be plus or minus 4, but obviously we can't have negatives, so it's just x equals 4. And you could go put that back in there and see if that would make sense. X equals 10 times 4, so 10 times 4 equals, which is 40, times 10 times 4 again, 40, equals the 32 times the 50, right? 32 times the 32 plus 18, and those both 1600 equals 1600. What about another one? Let's go here. Maybe we've got something like this. X plus 6, and this x plus 10. So we're going to have, again, outside 10 times the whole thing, 10 plus the x plus the 6. Can't tell you how many times the most common mistake would be to say 10 times x plus 6. That was when they intersect inside. When it's outside, it's the outside times the whole length equals outside 9 times the whole length. So 9 plus x plus 10. And we simplify, so we've got 10 times x plus 16 equals 9 times x plus 19. And we've got distribute now, 10x plus 160 equals 9x plus 171. Let's do it over the side. I believe that's right. 171. I'm going to subtract. I'm going to get x over here and subtract over here. I'm going to get 171 minus 160 is 11. Now I can again go back and check. If I have 11 in here, that means it would be 10 times 10 plus 11 plus 6 equals hopefully 9 times 9 plus 11 plus 10. So we have 10 times, what is that, 21, 27 equals 270 equals 9 times 9 plus 11 is 20 plus 10 is 30. So 270 equals 270. Okay, again, here is our formula, focusing down here. Out the tangent side squared, outside times the whole length. Here's one example that we did. Again, note the setup, outside times the whole length. And here is another example that we did. Outside times the whole length equals outside times the whole length. So it's very similar to I think that's enough examples. If you have any questions, I'm sorry. If you have any questions, let us know. Oh, since this is the last day, sorry, we do have these formulas. So again, when it's inside, P times Q times R times S. When they're two segments, not a tangent, outside, we have outside part times whole equals outside part times whole. And then lastly, we have a circle with a segment and a tangent. The segment side squared equals outside part times the whole times P plus Q. There is one other formula which we didn't go over the last 3 days, but I'll just say it right here. And that is when we have two tangents, you just get P is equal to Q. We've talked about that before. So whenever you have two tangents, P is equal to Q. Okay, have a good day.